All right, so I'm recording. Going back to this. No. All right, so derivative. So that's 9a. Definition of the derivative. Hang on, it's not moving. Okay, we'll start first with the average rate of change. So when you have a function that is defined, so you have your two variables y and x, you have a function which is in terms of x. The definition of the average rate of change for y with respect to x over the interval from a to b. So a is going to be less than b. They are going to be values on the x-axis, and is defined as the gradient of the line through 2 points a and b capital, and the y-coordinate is the function of that. Carly, do you mind turning that off?
So
yeah, you're not screen sharing at the moment.
Pardon?
You're not screen sharing at the moment?
You talking to me?
Yes. Yeah.
So you can't see my screen?
No.
Nope.
Oh. It's okay, I'm recording. I've got the recording on my end, so that's fine. Alright, so can you see that now?
Yeah.
Okay. Wait, I'm gonna have to continue. There's two of you that just turned up. Can you type in something in the chat to tell me that you just arrived? Because I need to update the role. No. 16. No, okay. Alright. No, I've got you and Joe. Ah, that's John. So I'm gonna have, let me update the role. Just gonna add John. There's another one. Oh yes, so Angel and John. So I'll mark you present. Let me do that. And I don't want to pause the recording, otherwise it split the videos, and I don't remember how to merge two videos. Okay, so let's continue with this. You have the screen, you have the sound. Am I recording? Yes, I am recording. Alright, so you have 2 points. The x-coordinate for each point are respectively a and b. The y-coordinate is f of a and f of b, because we're looking at the rate of change for the function f. And that's the definition of your rate of change, which is, if it was a straight line, it would be just the gradient between 2 points. This is the general rate of change, so it's applicable not only to straight line but to any other kind of function that we've studied. So it can be exponential, log, trigonometric, and a polynomial. Okay, so for example, just a simple skill application. You have your function, it's a quadratic. It's asking you to determine the average rate of change between 1 and 4. So you always take this smallest value to be your starting point, which is your a equals 1 and b equals 4. You substitute to find the y coordinates and you apply the formula. Okay. Alright, so we find the respective y coordinates for the first point, sorry, the second point and the first point. Make sure you write that in the correct order. You calculate the difference. Be mindful with the minus and the negative. Just be accurate with the application of operations with negative and positive number. And that should end up with -1. Yeah, that's fine. Okay. All right. So that was it. Hang on. Why am I doing this? No, skip that. That's not part of what I want to do. Okay. I could have mentioned it, but let's go on to the function. So let's say we look at the function again. So let's say you have our function here. You have 2 points. So that's my first point P, which we call A before. That's the second point B. What we're going to do here is, between those 2 points, we're going to determine the rate of change But the difference here, we're going to start moving towards what we call the instantaneous rate of change. So the idea is when that point, so let's say we fix point P, which is this point here. The other point is going to be variable because what we do is we use another parameter that we call H. And when this point gets really close to that one, that average line in blue will start to become a tangent to the function at that given point P. Okay? So point P, the function is x squared. P is, the coordinates will be a, respectively a squared. The point Q is a plus h. So the interval from P to Q, so if I annotate that, so from here to, let's say, here, that is h. Okay? So we determine the gradient, which is like this, the starting formula. We expand the brackets. We need to rearrange it and try to simplify it. So we expand the bracket, the a squared simplified. We divide by h. As long as h is not equal 0, we're allowed to. Did you say? I'm probably gonna have to. Abdullah, I need you to be muted. Is there anyone else? Is that better for everyone? Okay, so yeah, if you have a question, that's fine, just unmute yourself, but there's a little bit of background noise otherwise. Okay, so h, do remember when you have h over h and you simplify, h has to be different from 0. H is the interval, so it's not equal 0, which is fine. So Q will never be the same as P. It will get closer. Now that's going to give you 2a plus h. Okay. So that gradient, which is between the 2 points. Now h, it's going to be a parameter. What's going to happen here? Hang on. Is when we're going to make Q getting closer to P over here, what we're going to do is h is going to become 0, and we're going to use the limits. So when h approaches 0, so it's h approaching 0 when we use the limit notation, like that. 2a is independent of h, but h will become 0. So what we can say now is the gradient of the tangent at P is said to be equal to 2a. So that's what happens when Q becomes very close to P. Okay? So the limit notation, what I just introduced just before, for a given function f in terms of the variable x, what we're going to say is when x approaches a certain value that we call a, this is what the notation that we use. We write it right underneath the limit, LIM, so that's the not the acronym, I guess. And when x is converged towards a, you can simplify that as just replacing the function in terms of a. So for example, if you have this function, so the way here you read it is limit of f of x as x approaches 2 is going to be equal to 0.01. The way you will get this answer is by substituting that value 2 into your function. So that's probably going to be equivalent to use when you do your working out. It's going to be f of 2, whatever the function f is. You don't need to, it's not particular, it's just a general situation. Then it will be equal to 0.01. Okay. So for this, you're going to be practicing limit calculations, so it's a bit of algebraic manipulation. So with a function that is in terms of x, you apply the previous relation. Okay, so you have limit of f of x when x converges towards 3. You substitute x by 3 into here. That's a linear expression, so it's x plus 6, and that becomes 3 plus 6, that gives you 9. You can also do that with a function. Now it's a function in terms of x, but this time it's going to have also a h parameter, But now what you notice is we're not converging for x. X is going to be fixed, so we're going to leave it alone in that function. What we're doing here is we're making h converging towards 0. Okay? So anything you need to, as it's a fraction of a h, or anything that has a h term, you simplify. So all the h's crosses out. This one is just the power, so that goes down by 1. So what we left is what we have over here, 3x plus 4 minus h. Now h converges towards 0. You leave x alone, so the 3x remains unchanged. It behaves like a constant because you only affect h. 4 is also a constant in terms of h, and this becomes 0. Okay, so that simplifies to 3x plus 4. So I know it has an x variable left, but remember in that limit we're working on h. Okay, so just be mindful that that variable that when you calculate your limit, don't confuse it with the other variables or letters that are going to be used inside your expressions or function. Okay, on your CAS calculator, you can go through that. It's on the work example as well. So under menu 4.4, you have your calculus and your limit. Just hold on, I'm just reading the question. It's correct, that's right. No, 3x plus 4 will be the value for a specific given x. So if I go back to this, that is extracted from a rate of change. I don't want to go too much into it yet, but basically this is coming from an actual quadratic function. Okay, and what we're doing is you have a quadratic function. Again, remember what I'm doing here is we leading towards differentiation. I know in specialists you already covered the rules, but in methods what we're doing is we use the limit method to determine the derivative or the gradient of the tangent of a function. So for example, you're over here and I have a certain point I have on my parabola, and what I'm after is I want to find the tangent. Okay, so that's the graphical interpretation, but what we're after is actually we want to find the actual gradient value. Okay, now do remember that value that we have here, it's not necessarily a number, it's going to be a variable because we can slide this across. We want to find the tangent not as an exact value but as a variable in terms of x. As you move along the parabola, you can see that the gradient is going to change. Okay, so over here the gradient is going to be higher. So what we expect for the m value is not to be constant, but we want it to be in a new function in terms of x, and x will be your independent variable that you change over time over here. Okay, does it make sense? All right, so here, yeah, don't think about too much. I know it looks like a straight line, that's fine. What you need to when we'll do differentiation later, you'll find out that when you differentiate using the formula, not the limits, but when you differentiate a quadratic function, when the first derivative is always a linear function. The power goes down by 1. So the degree of a quadratic is 2. You minus 1, that becomes 1. So it's always going to be a linear function for the derivative of a quadratic function. Okay, let me read that question again. A tangent line. All right, for a, this is going to lead onto this. All right, you have two things here. All right, so for a line you need 2 points. You always need 2 points. Now when we did the average, the rate of change, so let's say this one, Okay, so you have 2 points here. When we move this point really close, so h becomes converge towards 0, and we use the limit today to do that algebraically. But geometrically, this point is going to slide closer to here, and as it gets closer, let's say I'll do it close enough but not at the same point, you can see now that line, if I join, okay, well, let's imagine it goes through those 2 points. You can see now that new red line will start looking like a tangent. A tangent, remember, whatever function you have, so let's say I draw something like this, and I want a tangent at this point. It's a line that is only just touching the function at that point. Okay? So we're doing that introducing limit. You will have to introduce a h parameter, and what you will do is you will create a limit like this. This is your average rate of change, and it will end up with an expression in terms of x. So there's two manipulations you're going to be doing. You're going to do some easy questions when you find an actual value, but as it gets a little bit more complicated and you get more fluent with it, it will start to become more an expression. Okay. So again, you can do that on your calculator. So you will enter your rate of change. You will specify h converge towards 0. So it's when it displays. I don't know if it's on the same next screen. Yes. So here you enter your expression, your ratio, or your numerator and denominator of functions in terms of x and h. And here you type in h, and here converge 0. That subset over here is optional. So if you wanted to approach from the left, you will put a minus here, and if you approach it from the right, you will put a positive. So for example, if I do, I think it's going to be covered a little bit later when we look at the if a derivative function is continuous. So if I do h0 and I put a positive, okay, what it means is you approach a point from the right, is everybody else lagging, or is that just Louis? And then you approach it from the left. Okay, but okay, that's fine. All right, so that's optional, and but you just keep that in mind for later. It's a different shaded gray. Okay. All right. Moving on, you fill that in. Let's fill that in, and you get the answer. Notice that it's in terms of x, so it's 4x squared. All right. So to summarize that, what we've done, covered at the beginning of those slides. This is your average rate of change. Okay. Here, what's hidden here is you have x plus h minus x. Okay, that x will match that f of x, so that's the coordinate of the first point. Here x plus h is the x coordinate of the second point, and will match up with the y coordinate of the second point. So that's your average rate of change. To determine the instantaneous rate of change, what we need to do now is introduce a limit, and we make h to converge towards 0. So that will get close to x. And then we can say the tangent line to the graph of the function f at a point a f of a. So that a, they replace that a from that x over here, which is fine. So for a point f a f of a is defined to be the line through a f of a with the gradient f prime of a. So this is your f prime of x, and all you need to do is substitute x by a, and you get the gradient of the tangent at that point of the curve. Okay, did you do that last year as well?
Yes, sir, we did all of this last year.
Okay, that's fine. All right, thanks, Elia. I mean, it's important. Just give me feedback. That's fine. All right. So what we did here is the fact that we introduce the average rate of change and we do the limit. This is what we call differentiating by the first principles. Now, when we do that with more complex function and you know how to differentiate, you won't do that systematically, okay? But it's an algebraic process that you need to be familiar with, as you might have a question on the exam 1, and on exam 1 as it is, you're not allowed to use a CAS calculator or your notes, so you will have to do an algebraic process, okay? So working out pen and paper and to figure it out, okay? Carly, for the first principle, it's important that you know how to do it by hand. When we, let's say for the application set, when you use the CAS calculator and you have all your notes, to differentiate, you don't use the first principle. You will straight away use the formulas, and it will be more advanced. More advanced in terms, using the first principles will be too much time consuming for you to use all the time. Okay, so be familiar with both. The first principle, we do that with simple functions. Usually, most of the time, it's going to be a polynomial function. So they will give you a cubic or, well, quadratic or a cubic. That's usually most common. If we move on to circular function, exponential and log, don't use the first principle. You don't have the skills. You don't need to know to do that in year 12. You will just use the formulas and the CAS calculator to differentiate. Okay? So here you have a function, it's a quadratic, so it's x squared plus 2x. Using the first principle, you need to determine, so you need to have 2 points. So your first point is a x f of x, and you have your point b, which is x plus h, and that one. So you determine your f of x is the same as your original function. F of x plus h, what you need to do is take that x plus h and substitute into your x to get a new expression. Alright, you need to expand it, expand the brackets, regroup the like terms if needed. No, maybe not yet. No, leave it expanded. The reason why is later on the terms will simplify. Okay, so this is your y coordinate of the second point. Then you use the expression of the first derivative. Okay, so the first derivative is limit of that f of x plus h minus f of x divided by h. So you substitute that with that whole expression. Now you can remove the brackets. Just be mindful when you remove the brackets here, because you have a negative, don't forget that this one will turn to be a negative. Okay, so you expand that, you're going to have an x squared. That x squared will cancel out with this one. Okay, and that 2x will cancel out with this one. Now, what if you've done this right? All you have left is terms that will have an h factor, or h, at least h. So h squared is higher than h, that's fine, and you have a h here because the denominator is an h, so it will simplify. The h will simplify here, and what's left will be, let me add a line for the working out. Before you do the limit, you will have 2x plus 2 plus h. Okay, but when you do that limit and you make h converging towards 0, you just substitute h into here, that cancels out, and what's left is 2x plus 2. So now what we did here, by using the first principle, if you have your function which is a quadratic x squared plus 2x, the first derivative is 2x plus 2. Okay, and no, h has to converge towards 0, because if we want that point B to get as close as possible to A. And how do we get x plus h to get close to x? Is by having h converging towards 0. That's just for the first principle. Okay? Now, in general, when we do limit, if we're not looking for the derivative, and I'll give you limit calculation, that h can converge towards anything, any value. But just to find the first derivative, we want that to be converging towards 0. Alright, so that's using the first principle. So again, you need to know how to do that for a polynomial by hand. Okay, so putting that aside, to help you to do that without using the first principle, there's a simple rule. Every time you have a polynomial, so if your function is x to the power of n, so we're going to look at a single term to the power of n, the derivative, which is f prime of x, is equal to x to the power of n minus 1, so you reduce the power by 1, and at the same time you add a factor n in front. Okay, so that's the formula. That only works if n is different from 0. Okay, wait, it doesn't, yeah, no, that's fine. I was thinking about the antiderivative, but that's different. Okay, now if n was equal to 0, you would actually have a constant. So those are rules that you need to be familiar. This is we're moving on to differentiation. So we looked at the first principles, is for you to manipulate algebraic functions and limit. Now for differentiation, polynomial, that's the rule. For a constant function so is anything that is not equal to x. So it can be well, excluding 0 as well, doesn't really matter, but any value, fractional, it can be an integer or a decimal, the derivative is equal to 0. Okay, now graphically it should make sense. So if I have f of x equals c, can you tell me what it looks like graphically? That, what I'm circling. It is a straight line, but yes, it is horizontal. And because it's horizontal, what's the gradient of the tangent? Or what's the gradient of that line? Because the tangent of that line is going to be itself. Okay? That is why the derivative of the tangent, which is the first derivative, is also equal to 0. Okay? Alright, a bit of rules about manipulation. If you multiply a function by a constant, okay, sorry, I need to go back again. Elia has a question. Wait, what did you say about the gradient? Okay, so if I draw a function that is curvy, the tangent is intersecting a straight line at one point. Okay, now if I have a straight line and I pick this point, what is the tangent to that straight line? Is actually itself. So it's going to be something like that. Alright, so for a linear function, by the way, that goes back to this, for linear functions, so for example, if I do this, f of x equals x, well, the first derivative is going to be, what's the power here? It's going to be a 1, so you write 1. Well, you don't have to write it, but I'm just doing the working out. So it's 1 times, because I'm applying the formula that I had above, so it's going to be 1 times x to the power of 1 minus 1. And as you remember your index laws, x to the power of 0 is 1, so it's going to be simplified to just 1. So the derivative of a straight line is going to be a constant. Now, to generalize that to a straight line like that has a gradient different from 1, if I multiply by a constant, then the first derivative is equal to the derivative of the constant stays in front, and you just differentiate the other factor that is in terms of x. Okay? Also, when you add or subtract, the first derivative is you differentiate each term, you add them or you subtract them if needed. Okay? So the idea is when you have a polynomial, usually you won't have x to the power of n on its own. You will have different terms of different powers. So you can have, for example, x cubed plus x squared. So you will differentiate your x cubed, you will differentiate your x squared, and then your final derivative will be the sum of the derivatives you calculated earlier. Okay? And that would be a typical example of that. Okay, so the second rule. So this one with a multiple. Alright, so f of x is equal to a constant times a function. So for example, so I'm going to use this example. F of x, so I'm going to call that g. G of x is equal to x. It means the derivative, so the derivative is equal to 1. So if I write f of x, you know what, I hate using this. Can I use my other cam? So here, if I write I need to go back to the other screen. So if I go to and I write g of x is equal to x, the first derivative is equal to 1. Okay? Now using the multiple, I say f of x is equal to, let's say, 7 times x. Okay? Then what you would have is 7 times g of x. Now the derivative of f, 7 is a constant, so 7 doesn't change, and you multiply by the derivative of g. Okay? So that will simplify. 7 doesn't change, derivative of g prime is up here, so that's going to be 1, so that equals to 7. Does it make sense, Minerva? Okay. Kali, what's the question about the fog? Oh, fuck. F of g. Okay. Well, I haven't done that yet. This is just a product. It's not a composite or it's not a composite function. Okay. All right. So moving on. All right. So here it's a difference and a sum. So here you have a difference, you have a sum and a difference. You look at every term. You differentiate using the polynomial, the rule for x to the power of n. So let's say I start from the easier one, so something like that. So that's my f, and I want to find the first derivative. By the way, if you were brave enough, you could actually do this using the first principle. That will take you quite a bit because you will need to expand that x plus h to the power of 6 and the x plus h to the power of 3. By hand, it will take a long time. But that is the proofing, how to prove that the derivative is actually indeed equal to that. Obviously, using the formula is much quicker. So do remember, you have a constant. The first derivative is 0, so that should, you put that out of the way. The 2x squared. So Minerva, what I was explaining before, the 2 is a constant. Because it's a constant, you write the 2 in front. You don't change it. Now you look at your x squared. The derivative of x squared is 2. So you multiply by 2. X squared, you minus the power by 1. That becomes x to the power of 1. And that gives you 2x. 2 times 2x is simplifies to 4x. Okay? Alright? And then you do the rest. So x to the power of 6. Don't forget the negative here. There's a negative that transfers. X to the power of 6, you bring down the 6 as a factor, and the power, you subtract 1, that becomes a power of 5. Okay? much quicker on the calculator. If you have a CAS calculator, you need to answer multiple questions. Unless you can do it quicker in your head, do that. Or you're not certain and you want to verify, use that. So it's under menu, calculus, derivative. It will be x left as a variable, and you will enter the, hang on, it will look like that first. So you will have d over d. You have a box up here, you also have a box down here. You write your expression in terms of x, and the denominator you need to specify which variable you differentiate in terms of. Okay, so here your independent variable is going to be x. You write x, but you could change it to anything. It can be u, it can be a. So just be careful. All right, and then you get the same answer. All right, another example, just worded slightly different. For the curve f of x equals 2x squared minus 5x plus 4, find the gradient of the tangent line to the curve at the point 1, 1. So to find the gradient, you find the first derivative, which is what we did in the past example. But then for the point 1, 1, it's not going to be a function for the gradient. It's going to be an actual numerical value. Okay, so first you do the first derivative, so that's going to be 4x minus 5. You substitute x equals 1, that gives you negative 1, and then you can say the gradient of the tangent line at the point 1, 1 is negative 1. Now I don't know if it's mentioned later, but I want to do that right now. Can you tell me how you figure it out, the equation of that straight line, of that tangent? Anyone? No one? It has. Okay. So what I want you to figure it out is the equation. So it's a straight line. The tangent is a straight line. So it's in the form of y equals mx plus c. That is what you have for a straight line. For this particular point and this tangent, what is its equation? How do you figure it out? You have the coordinates and you have the gradient of the tangent. Correct? You have the gradient. Yes, that's fine. Okay. Now, there's two ways you can do it. You can do it this way. So you substitute the coordinate 1, 1 into here, or the other way is you do y minus y1 equals m bracket x minus x1. Okay, fairly similar, whichever works the quickest. The plus c expression sometimes might be quicker. Now if the line goes through, there's a situation where it might not be ideal, is when the c is equals 0. No, that's fine, that will work as well. Okay, all right. Now if you have the tangent, can you tell me the gradient of the normal to the tangent at that point? So let me say that, type it in, the normal. What's the gradient of the normal? Let me spell that with my mouse. Normal. It's with the E. So what's its gradient? With capital N. That's usually the notation. Any of you remember? Yes, it is 1, but how did you get that? Actually, I'm just going to tell you. I need to move on. the normal and the tangent, they are perpendicular. If you have two straight lines that are perpendicular, if you multiply the gradients, it's always equal to -1. So that's going to be -1 divided by the gradient of the tangent. Okay, -1 divided by -1 is +1. Okay, it's just a reminder about the things that you've done with linear equations. Okay. All right, moving on. Okay, Leibniz notations. Just a little bit of notation with the first derivative. So we looked at how we label the first derivative is f with a little dash. Okay, so we have f prime like that. Another way you can write it out is this way instead. So that's your function f, or we can call it y, because it's defined as y equals x to the power 4, and it's in terms of dx. By the way, that's a comma, that's not a dash. So dy over dx is the same as f prime of x. So you have this notation, you can also have that notation, and at the end the calculation is still the same as what we did before. Okay. Just a reminder as well, when you have the gradient, so do you remember your gradient is also your adjacent over your opposite? Okay, so the how does it work out? What's important here? It's gonna be, but that's the important part. So if you have your gradient, it's equal to tangent of theta, and if you apply the inverse tangent, make sure you have your Cars calculator. Probably you will use your Cars calculator unless it's an exact value that you know. So for example, tangent theta equals let's say √3. You need to remember that theta is pi on 3. Okay. But if it's something that is kind of weird, a decimal, so tangent theta equals 2.5, what you would do is theta will be inverse tangent of 2.5. Okay, now your angle will be either in radian or degrees, or depending on the unit that you have set on your CAS calculator. So just be mindful of that when you use your inverse of circular functions. All right, so that's fine for that. Okay, I think it's coming on the next slide. No, that's fine, we have that. So that's the visual representation. So application of what we've done before. So you find the coordinates of the point of the curve with the equation y equals x squared minus 4x. Now we know the tangent line makes an angle of 45 degrees with the positive direction of the x-axis. So first you differentiate. So that's your x squared minus 4x. You get 2x minus 4, which is a variable expression in terms of x. Because you have your angle, you know that the gradient of the tangent has to be equal to tangent of 45 degrees. 45 degrees, remember, is doing your left hand. How does it work out? So you do, I don't know, I'm not facing that way. So 45 degrees is here. You need to fold that, and that's the 2, and you end up with you doing the ratio. Okay. So that gives you 1. So you substitute that gradient into the left hand side of that expression, and you solve for x, and that gives you the x coordinate. You need to substitute into your, go back to your y function, substitute back into here, and I will give you the y coordinate. Okay, and that's where you get over here. All right. Exact form, improper fraction, that's fine. Okay. I think I mentioned about decreasing and strictly decreasing function. There's a shorter way to do that. Instead of looking at the rate, so for example, when a function is strictly increasing, so you start from x1 towards x2, meaning that x2 is greater than x1, or x1 is less than x2. What it implies is f of x2 is going to be greater than f of x1. What it also means, what you could do is, if you calculate your first derivative, which is when you do the average, it's a rate of change, and the rate of change will relate to those differences. And it will have, if it's positive, then you know that the function is strictly increasing. So as you get better knowing how to use first derivative, this is a quicker way to determine if a function is strictly increasing or decreasing instead of looking at your inequation of the y coordinate. Okay. All right. Now, graphically, so let me go back to this because it relates a little bit to that. So if you found the derivative is positive, your function is strictly increasing. So let's say I'm looking at just this bit here. Now the derivative here is also the gradient of the tangent. Okay. What you do then is you look at your function here, and what you need to do is to imagine as you move along the curve, what does the tangent look like? So let's say I pick a point right over here. I can see my tangent is going that way. What is the sign of the gradient? Because it's going upwards, it's going to be positive. And then you're going to have to exclude those ones. So for example, let's say you pick that one as you're not experienced, you draw your tangent from the left to the right, the line is going downwards. It means your function is going to be decreasing. So here it's telling you find, for the graph opposite, find the values of x. For the derivative to be greater than 0, notice that it's not equal. As it's not equal, you need to exclude those points here where the tangent is horizontal. So that's horizontal and that's horizontal. So it's between -1 and +5. You read the coordinates, okay, and you need to exclude the boundaries. Okay. So here we go. You have your solution like that. So it's in an equation. Yep, that's fine. Or the way they write it, it's equivalent. Okay. All right, that's it. Questions?